So today we'll go into the second part of QSSP, which I'll be covering first, because it is pretty independent and a pretty tiny section compared to the first. I'll be traveling the second part of QSSP, which is basically magnetism. Uh, so the idea today is basically to present the tutorial on magnetism to understand the theory. So, and the structure will be in such a way that we go through the tutorial without paying too much attention as to what the question demands. So in the sense, we'll try to analyze and arrive at different aspects of the theory without answering question. Of course, like the questions are here, and you can pause the video and have a look at the question, or find it attached. Anyways, so this is yeah. Anyways, just an introduction to the course. This is QSSP, Quantum Solid State Physics, which I'm covering as part of M1 General Physics at University Paris Saclay. This particular course was taught by Professor Agnes Bartholomew. So yeah. Anyway, so all the course notes and everything is credit to her. Let's start with magnetism. So magnetism is okay. So what we're going to do today is we're going to study the story of magnetism, and looking at paramagnetism, ferromagnetism, and anti-ferromagnetism. We will just try to look at the various aspects of magnetism, and the three key players, the three key parameters that you want to find here are the external field. Okay, so you can have an external field, and or you may not, and based on that, the magnetic the samples that you're trying to observe, the things that you're trying to measure, have different take up different properties. And second thing is temperature, and this temperature is like we will define such a thing as critical temperature, where magnets start changing their properties. And then third thing is your inherent susceptibility, which is basically the response of the magnetic field, like of the sample to the external magnetic field, right? So that is the ratio of the magnetization to the external field, like the field that is generated by this particular magnet under the presence of an external field. This particular ratio is something that is also of interest to us. So given by susceptibility, so given these three key players, temperature, okay, yeah, you have energy, right? You have the magnetic moment, or the fields, both internal and external. Then you have temperature, and then you have the energies associated with it, right? So these three key players is what we're trying to analyze and describe, and get relations between. So let's first look at paramagnets. Okay, also in the paramagnetic and ferromagnetic cases, we will look only actually even anti-ferromagnetic. We will look at cases where there is only contribution to the magnetic field because of the spin of the atom, or the molecule. That is one thing. So only spin contributes. There is no orbital angular momentum. So therefore your J, which is your new quantum computing variable, which is J is equal to S plus L, that is the L is 0, so J is equal to S, which is h bar by 2 here, and your ms is indicates the spin, basically the magnetic the factor of magnetization due to the spin, which is plus minus half. It can be oriented up or down, and we're dealing with the z axis, which is okay. So why the z axis? The idea is fundamentally magnetism is dipole phenomenon. That means that it can be described by 2 points, right? And when you say 2 points, which is the north and the south pole, when you say there are 2 points that are describing, you can automatically align the points along an axis, along a line. So essentially that becomes your magnetic axis along which you're trying to describe your dynamics. So you're dealing with the z-axis here, and it's called OZ axis, right? For the convention with respect to the hand rule, like all that kind of stuff. Anyway, so and one more thing is the Landau factor, which is 2 here. It is your Landau factor is basically the factor of contribution of your spin to the net magnetic moment. So why is it? So it's because spin is extremely localized. It offers like double the contribution as your orbital angular momentum causes. So when you and like for orbital angular momentum, g, the Landau factor is 1, and for spin it is 2. And when you have like a mixture of both orbital and spin, like when there is a coupling, you have a little more complicated system. But yeah, so you have, yeah, so essentially you can derive it from Dirac equations in the magnetic field, right? Moving on, the magnetization in the along the z-axis is given by plus minus 2 for okay, so we are considering a paramagnetic salt with an atom per unit volume with a localized magnetic moment mu along the z-axis. So your magnetic field magnetization is given by plus minus 2 mu m b mu bm, right? So m is the factor of contribution, that is spin half, right? Like, so it's the factor for the Planck constant, that is the energy carried by the spin, and times the Landau factor, right? So mu b is the inherent magnetic moment associated with that particular atom, right? So then you have your energy given by minus mu into mu naught h, where mu naught h is the strength of the external field that is applied, right? And mu here is the localized magnetic moment, right, of the atom. So E is equal to minus mu naught h. And what we see that for the external field, the applied field is 0. You see that there is a degeneracy, right? That means that for a paramagnet, it is perfectly non-magnetic if there is no external magnetic field applied. But however, when an external field is applied, it shows a weak response to the external field, as we will see. So now when h is equal to 0, you have like basically you have magnetic moment which is the magnetization, which is 0. Okay, and you'll see like you just calculate it with respect to the spin, and you actually see is plus minus plus mu b, and mu b is it goes to 0, right? So our temperature is when external field applied is 0 and the temperature is 0, so your mu b is here, right? And that means that the electrons are occupying the lowest degenerate state, right? Now for as you go increase your temperature, what happens is you're exciting some of the electrons, so they occupy a split state. Some will spin up and some will spin down. So associated with spin up and spin down, you have because spin up is directly like So spin up is parallel to the magnetic external magnetic field, and spin down is uh, anti-parallel. So when you have this configuration, you essentially have you see that for like large temperatures, you have an equal splitting into and like higher and lower energy state, right? So why like that is you have the same number of electrons occupying pin up and pin down. Why is this so? Because it is basically like as you increase the temperature, is the equivalent to saying increasing uh, the randomness of the system. And when you talk about this, just it's simple to look at an analogy in a more classical sense, which is basically if you increase the temperature, it's like you okay. So let's just consider a system like a box filled with marbles, black and white marbles. Black is like spin up and white is spin down, and then you shake it, right? You shake the box and then uh, you keep it down, and the probability that if I'm trying to pick a marble out of the blue from any random point in the box is going to be the same. So it is going to be the same for black and white, because black and white inherently have no difference except like the orientation of the spin, right? So the masses are the same, the electric charges are the same, everything else is the same, so it's nearly identical, right? So we say that the number of electrons of spin up and the number of electrons to spin down is essentially the same across the assembly. Okay, and so I also note just to clarify one more thing. It is not per se. So since we are dealing with separate like atoms, different atoms, and it's an assembly of different atoms, we can say like that there can be a parallel uh, arrangement of spin. So it doesn't necessarily have to follow the Pauli principle is not involved here. The Pauli exclusion principle is not involved here. Like you can say that neighbors can have the same orientation of the spin. They can have. Okay, it's very possible. But like as you increase the spin, like I mean as you increase the temperature, you have like an equal and like up and down arrangement, some sort of arrangement, right? So is because it is different atoms, there is no Pauli exclusion principles here, because so it's like it's better not to get confused in terms, especially if you're thinking along the lines of like n1 and n2 being equal, like how is that possible, etc., etc., right? um, Okay, anyways, moving on, n1 is equal to n2, so that means the net magnetization is the number of particles with spin up and the number of particles with spin down, and because they have like opposing values, the overall magnetization is zero. So this sample at large temperatures also has a magnetization of zero if there is no external applied field. Now we define the Zeeman energy, which is basically given by integral here, and since we are considering the density of energy density of the Zeeman energy density, we divide the whole thing by volume, and it's basically the same. So you have minus mu naught mz h, where h is the external field, mu naught h is the strength of the external field, right? Now so what happens, so now you see things taking shape, right? You see that because the electrons occupy different like energy levels, there's an energy gap that is generated, and that is given by 2 mu naught mbh, right? So now the energy of state 1, which is like your spin up state, is given by mu z is equal to mu b, and EB is equal to minus mu naught mu B H, right? But however, for spin down, you have mu Z is equal to minus mu B and EB is equal to mu naught mu B H, right? This is signs flip, right? And now let's look at a probability density of like the let's try to find out the number of these particles, right? So for that we need to define a probability distribution, and to define a probability distribution we use the Boltzmann distribution, which is probability of finding a particle in state I is given by e to the power of minus the energy occupied by that state, like the energy of that state, and divided by kBt, which is the Boltzmann distribution. And this whole thing is like, of course, has a normalization factor or like a partition function z. So we'll try to so because the sum of probabilities is 1, that is you find the electrons with either spin up or spin down, okay, and you have P1 is given the probability of finding something in spin up is given by e to the power of minus e to the power of mu naught mu BH by kBT, and similarly for P2. And then when you sum the probabilities and normalize it, you find out the value of z. You get this whole expression, and you find out the value of z, which is 2 cos h of mu naught mu B h by kBt, and we'll call this term as x, just to simplify the next step. So now if you want to find the number of particles in each state, and that is given by npi, which is the total number of particles times the probability of finding the particle in that particular state, and yeah, so you get n1 and n2, right? You get a function of n1 and n2. Now when we calculate magnetization, we find out the net magnetization of the sample. Like, okay, note that after you're talking about after you start talking about probability of state with energy EI, right? You are introducing an external field H, right? In the previous case where we found out that N1 is equal to N2, right, that is, there is no external magnetic field. Now we are applying an external magnetic field, and we are seeing how what happens to the electron or the atom. So now we are let's calculate magnetization. You can sum it as you can like simply find it out the summation of the contribution from spin up into number of spin up, contribution from spin down into number of spin down. So you have this, and you find out that this equals n mu b, which is the n is the total number, mu b tan h, the hyperbolic tan of mu naught mu b h by kBt. Okay, fair enough. And now let's try to do something here, which is basically we look at okay, so this is a numerical where we're trying to find given your magnetic field as mu naught h is equal to 1 Tesla, and at a temperature of 300 Kelvin, you want to find out what the x is, right, what this factor is, right? So once we do that, we see that it's at around 300 Kelvin, x is much lesser than 1, and therefore the next immediate step that we can take is we introduce a Taylor expansion, right? When we introduce the Taylor expansion, we find we approximate tan h to be tan h of x is equal to x, right? Okay, there should be an x after the tan h here, but yeah, tan h of x is approximately equal to x. So your magnetization is approximated to n mu b x, and your n mu b mu naught mu b by kbt, it is a constant. All these terms are constant for a given system that you're studying, and only your h can be changed, right? So basically that gives you your susceptibility. So we have arrived at a formula for susceptibility already, and since your susceptibility is given by is the function of temperature, you have arrived at the Curie's law, right? And then you see the graph here to just to visualize the whole thing. Also, with magnetism, it becomes extremely important to be able to visualize how these quantities are changing with respect to each other. So apart from the numerical relations, mathematical relation, it's also extremely important to have a graphical understanding of what is going on. So I'm particularly weak in translating it into graph, so I should work a little more on that. But anyways, that's me. Now, so we're done with the paramagnetic example, and now let's move on to ferromagnetism. Now, for ferromagnetism, we have the same things as before, the same ideas and principles as before. The only thing that changes is, right, so if there is no external magnetic field that is applied, okay, and if there is a below a certain threshold temperature, right, you have a weak magnetization of the sample. So the sample is inherently a magnet, right? It's a permanent magnet. So you have so within certain limits, it's a it's an inherent magnet, right? It has its own magnetic field generated by its molecular arrangement. So we call this the internal molecular field, and to deal with ferromagnets, we use the molecular field approach, right? Okay, so now magnetization along z-axis is given by same 2 mu b ms, which is plus minus mu b, and again we're considering only spinness, and no orbital momentum. So your hm, and this is the inherent inherent magnetized magnetization, right? In the hm is the magnetic field, internal magnetic field, and m is the magnetization of the sample itself. So hm is given by gamma m, and your h interaction is given by h plus hm, right? That is basically your your applied field plus the internal field. That gives you the total magnetic field, right? So now your magnetization is equal to n mu b tan h, the same formula as before, except that you replace h by h int, which is h plus gamma m, right? So when you do this, we note that in the paramagnetic region, that is, your temperature is much larger than the critical temperature, right? So we see we will arrive at the critical temperature soon, but so your for kBT is much larger than h, then your tan h is approximated to same, you have the same approximation, right? Because this becomes, for kBT is very large and h is very small, so this becomes much lesser than 1, so you can do the same approximation as before. And given that, now let's look at the magnetization. Okay, nothing, yeah, so you get rid of the tan h, And once you do that, and then you do some algebraic manipulation, you end up getting m is equal to n mu naught mu b square by kb, h by t minus n mu naught mu b square by kb gamma. So we call this term here as c, and we call this term here as theta, which is basically gamma c. Now we can define your m is like we have m magnetization is equal to susceptibility times h, so times the field. So susceptibility is defined as c by t minus theta. Okay. So the susceptibility itself changes with respect to temperature here, which is, I mean it's like it has a it doesn't change with respect to, it doesn't only change with respect to temperature, but then it has a critical temperature where your susceptibility blows out to infinity, right? And this critical temperature is given by theta, which we see has the units of temperature, right? So so x is given by basically x is given by c t minus theta, and h is out there. And your critical temperature is defined as c gamma, right? Which is this whole thing. That is so when you have this whole thing shooting off to infinity, that is your critical temperature is c gamma. So this is the paramagnetic regime is like above a certain temperature. So for a temperature above T critical, the Curie temperature is called the Curie temperature, right? So the above the Curie temperature, your ferromagnet acts just like a paramagnet, which is it is responsive to an external field, but it has no inherent magnetic field, right? But below the temperature, it has a certain magnetic field, magnetic properties of its own. So then, right, yeah. So now we'll look at what is happening below the Curie temperature. So below the Curie temperature, there is no external. We consider there is no external magnetic field, and there is just an internal magnetic field, right? At first, to make life easier. So yeah, the m is given by n mu naught tan h gamma m, right? Mu naught mu b square by kbt, and hm, which is the internal field, is given by gamma m as before. And now let's try to understand how this is varying with respect to this, like, well, because now tan h, the factor inside of tan h is no longer how do you say, it's no longer very small, so you cannot do the same approximation as before. So what you do is you instead define tan h is equal to mtc by t, where okay, so you define a small t, which is the ratio of tc and t, and you define m, which is small m, which is which is the magnetization by the number times the internal magnetic moment. So this is, so you calculate your magnetization and you take it, you do your Taylor expansion. So as m by t tends to 0, which means your m is very small here. So now what you have is m is equal to t by m, and so therefore you have m square is equal to t, therefore m is equal to root t, which is basically root t c by t, the the ratio of the Curie temperature to the current temperature. So that so your magnetization is inverse squarely dependent on the temperature. So you have a graph here, and then like what we do here is we take the first order Taylor expansion. So far we did this is the 0th order expansion, but and then like this, yeah, so yeah, we take the first order Taylor expansion here. And okay, so this is something that I still don't understand here, especially the m is equal to t by m, and how so that's one thing that I need to figure out, but it'll take some time. So anyway, so um, but for this case, so yeah, I just need to pay a little more attention to the limits, and if you can help me out with this, maybe I don't know. Yeah, that'll be awesome. But anyway, so and if I find out what exactly is happening, I'll like of course get back to you. Just this Taylor expansion got me a little confused. So now let's look at this Taylor expansion, and then you basically get this m is proportional to t minus tc by tc to the power of 1 by 2, and this makes a lot more sense actually, but I don't understand what is happening here. Like it's supposed to be like yeah. So anyway, so you have we trust the math here, and moving on. We consider something called as the energy exchange energy. Okay, so what is exchange energy? So when two neighboring atoms are like when the two neighboring pins are interacting with each other, right? So we consider what the cost of energy, or like the energy that it takes for one pin to like exchange with each other. It's basically given by some factor J exchange, which where I mean we'll work on this more, because this exchange energy introduces certain ideas of like um, cost of the magnetic field, and like it introduces harder limits as to the amount of net external field that a magnet can take, etc., 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 right? But we'll cover that in the future tutorials. But one thing here, we introduce exchange energy given by minus 2j time s1 times s2, and for exchange of like one spin with z neighbors, you have minus 2 and this you have z by 2, and for n spins with z neighbors, you have this minus 2j exchange s1 zs into n by 2 times n, and this half factor in this equation come because of the exchange interaction, so being considered only once, and you don't want to count it twice, right? You don't want to count because it is like one interaction, one exchange energy for two things. Like you don't need to subtract one, you don't need to take both the permutation, right? You can like discount half of the total permutations there, right there. Okay, so now your and the interaction energy is given by minus n mu naught mu hm, which is uh, your neighbor like okay, so this is the net like the interaction energy that is generated by a particular atom interacting with the field, like with the neighbor. So now we get an expression for this. So now what we want to do is we want to set up a limit in which interaction energy is basically the same as the exchange energy, and therefore we do some algebra and we arrive at the relation between your J exchange. We arrive at the relation between mu naught hm and J exchange, and we can also express your Curie temperature in terms of n mu naught mu b square gamma by kb, and which can be further expressed in terms of J exchange by 4 kb. So here gamma is J exchange by 2 n mu naught mu b square. Okay, so yeah, it's a lot of algebraic manipulations, and the idea of like exchange energies and interaction energies is something that I'll go more into detail in the next uh, next tutorial, because it show why we will actually, we need to understand why we are talking about energy in the first place, right? So far it's just about like the behavior of the magnetization with the temperatures and with like the external field applied or not applied that we are concerned about basically. But soon we will have to deal with why like certain like cost, like we'll play around more with the idea of exchange and interaction energy, right? So right. Yeah. So right. So then we also figure out like we arrive at a relation between your mu naught hm and your Curie temperature. The the magnetic field and the Curie temperature, right? Uh, that is with ferromagnetism and paramagnetism, which are fairly simpler cases, because paramagnetism immediately has an external like it just has a simple linear response to the external field, and ferromagnetism, it has its own internal magnetization um, up till a certain temperature, and beyond the temperature is basically paramagnetic. So it's pretty simple. But now we consider anti-ferromagnetism, which is basically given as so. So now this anti-ferromagnetism is given by this. So we consider a chain of two n atoms, where these atoms all are aligned in, like the neighboring atoms are aligned with opposite spin, right? So which means the opposite magnetic moment as well. So now we have Mn is minus G mu B Sn. So which is N is the index of which particular atom you're trying to talk about, and U is the okay. U is your exchange energy, okay, and the J factor that we talked about earlier is basically less than zero, which is it's negative. So you see that the idea of energy, like the minimum energy, is actually not to be misled by this minus sign here, but it's actually positive. So you say when you are looking at like spin up and spin down, you might get confused with the negative signs. So just pay attention to the sign here. So you can define your exchange energy as follows, and at temperature 0 you have the spin of all 2p atoms given by plus s, and 2p plus 1, that is all even is plus and all odd is minus, and this kind of minimizes the energy. Okay, so we want to find out what minimizes, what arrangement of like this atom minimizes energy, and we see that U is equal to minus 2j Sn into Sn minus 2 and Sn plus 2. So it is the neighbors of Sn, right? Sorry, Sn minus 1 and Sn plus 1. I need to change this one here. So it's like you have an atom here, and then you take the immediate neighbor, left and right neighbors, and that gives you your interaction energy, right? So your energy of the central atom interacting with the left or interacting with the right. Okay, forget that this is not Sn is good. This 2 has to be 1 here. Let's make a correction right now. Okay, Right. Yeah. Yeah. Okay. So yep, this is done. Right. So this is one here. Right. And for this to be minimized, we need to find out the maximum value of this. Right. And we find out that it is Sn is antiparallel to Sn the odd atoms. Right. So we find out that this in fact is the best arrangement for uh, minimized energy, which is the stable solution of the system. So now we find U is equal to 2js into 2s, and which is algebra here. And now what we do here in the next step is we consider the and like not perfectly anti-parallel arrangement, but we consider some deviation by angle phi1, which is usual, right? Like if you consider a random sample, of course all spins are not going to be perfectly anti-parallel, so there is going to be some sort of like a an angle which is likely to be expected. So now we want to find out the stable solution for this, right? And we calculate the E of 2p and E2p plus 1, and we get the interaction energies, and we get the exchange energies, etc., etc. And we calculate the net energy of like 2p plus 1 and 2p, which is basically the sum of exchange and interaction energies, and we find out we have two equations, right? Now the total energy of the system that we are considering is the summation of all exchange energies of both odd and even atoms by 2. Okay, because again this two factor comes because of same permutation problem that we talked about earlier. And then the magnetic energy of contained by each atom, each odd atom, and then each even atom along the z-axis, right? So now what we do here is basically we try to figure out the derivative with respect to phi1 and with respect to phi2, and we find out that is equal to 0. This is basically the minimization of energy that we're doing with respect to the angle, and we want to find out what the optimal angle, right? So right, theoretically the optimal angle is supposed to be parallel and anti-parallel. So we find out that it is phi is equal to pi by 2. Okay. So first we find out that phi1 and phi2 have to be equal, and then we find out that phi is equal to pi by 2. And this ratio here, sine phi, we declare it to be minus h by hc, where h is the critical magnetic field. And okay, so it's defined. So and we'll go into this from here. We'll take it on in the next step, because well, I want to get a little more clarity on this, but essentially this covers, okay, so we understand to a certain extent what it means to have different types of magnets, how their energies and their moment and their magnetization is characterized at different temperatures. And we also found out how to get this idea of like a Curie temperature, and in both para and ferromagnets. Wait, no, sorry. How to get this idea of like Curie temperature in ferromagnets, and why, like how this like expansion of your edge as sum of like internal and external fields gives you this kind of splitting of temperatures. Okay, so and that defines your Curie temperature, right? This is one of the most beautiful ideas in magnetism, because you suddenly, okay, you ideally expect that like the magnetization should not depend, like the magnetic property should not depend on the temperature, but or like even if it does, it has to be like I don't know, somewhat random, but like you see that it's beautifully given by the Boltzmann distribution, like the Boltzmann temperature, and like so when you talk about these things, right, when you talk about the energy, right, in terms of magnetism, in terms of the magnetic energy, you actually find out that like there is a critical temperature that can be established, that is the Curie temperature, and beyond which ferromagnet acts as a paramagnet basically. So and yeah, so the main idea is to just get used to representing like being able to write down your moments and your fields and everything in the expressions of everything in like a comfortable and smooth manner. And then like the next step is to evaluate your Taylor expansion. This is something that I'm having a little bit difficulty in, that I get lost in sometimes. I'm still like not very familiar, but yeah. But beyond that, it is more or less simple algebraic substitutions and relations and all of that come into picture, and like building the whole, bringing the whole picture together and connecting different dots. So and then like the next time we will continue with this, we will like try to understand what this interaction and exchange energies are, and with that hopefully we'll be able to tackle on more problems and then understand a much wider range of magnetic behaviors. But yeah, that's it for today, and hope to see you guys soon. Hey, anyways.